Good morning and welcome to this video as I call differential equations 2. We've already talked a little bit about differential equations and we've solved some differential equations. And the types of differential equations we've looked at and solved are in this form. We have a dy dx equal to 5x squared plus 3. And we may have an initial condition of y of 0 equal to 4. And we solve that. If you remember how we solve these differential equations, we separate our variables. We get our dx over onto this other side by multiplying both sides by dx. And then we take the antiderivative of both sides. We end up on this side, the antiderivative of 1 dy is simply y. And over here we get 5x cubed over 3 plus 3x plus c. We use our initial condition right here, y of 0 equals 4. We plug in 0 for x, 4 for y. And we solve for c. And we see in this case that this goes to 0 and this is 0, so 4 is equal to c. So my solution to this differential equation is y equals 5x cubed over 3 plus 3x plus 4. So that's what we've done in the past. Now we're going to just turn it up just a notch, just a little bit. Here's example 2. We have dy dx, still in the same differential equation form, is 5x over y. And our initial condition, or our point that we're going through, is this: y of 1 equals negative 1. Now, you should notice something right away compared to the ones that we've done already, is that we have a y and an x over here, and not just x's. So, what does that mean? Our process is the same, our procedure is the same. We separate the variables, we get dx over here, but now we have to get y on this side as well. So I'm going to multiply both sides by dx first. To get 5x over y dx. Now I'm going to multiply both sides by y to get y dy equal 5x dx. That's why it's called a separable differential equation, because we can separate the variables. We have y's and dy's on one side, x's and dx's on the other. So we take the antiderivative of both sides again, and we just take the antiderivative like always. What is the antiderivative of y? It should be y squared over 2 equal to, over here we have 5x squared over 2 plus c. At this level, we now solve for c. Before we do any other mathematics, we solve for c. So we put 1 in for x, negative 1 in for y. So we have negative 1 squared over 2 equal to 5 times 1 squared over 2 plus c. Negative 1 squared is 1, so we get 1 half equals, this becomes 5 halves plus c. We subtract both sides by 5 halves to solve for c, and we get c is equal to negative 4 halves. So at this level, and you'll see I'm moving up here, at this level, now we're going to put y squared over 2 equals 5x squared over 2 minus our 4 halves. I want to solve for y. So I'm going to get y by its lonesome. So what do I have to do? I have to multiply everything, both sides, by 2. So we're going to do that, and look what happens. We get y squared equals 5x squared minus 4. Now we're going to get rid of that y squared. How do we get rid of a squared? We take the square root of both sides, and we get y is equal to plus or minus the square root of 5x squared minus 4. However, there's only one correct answer to the solution to this differential equation. It's not the plus or minus. There's only going to be one. Can you guess which one you think? Or not guess. Do you know which one it's going to be? Is it going to be positive, or is it going to be the negative? If you thought it was going to be the negative square root of 5x squared minus 4, you would be correct. And why would you be correct? Because our initial condition says that it's going to go through negative 1. So it's going to have to be below that x-axis. So it's going to have to be represented by negative square root. If this were a different initial condition, maybe this were a positive value. If this were a positive value, then it would be the positive square root of 5x squared minus 4. Okay, so here's the difference. There's a y here. Now we're going to get into some more complex types of differential equations, just involving more skills in antiderivatives more than solving it. So again, separate the variables, take the antiderivative of both sides. Everything has remained the same. The process or the procedure has remained the same. Here's example 3. We have dy dx equal to y minus 1 in the numerator over x, and we have a condition that x cannot equal 0, because look what would happen if x were 0. Yeah, that's good. Now look how I'm writing this. I'm going to do this like at AP exams, you will see. We have written in class y of 2 equals 4. Now I'm writing f of 2 equals 4. Same idea. Same idea. Just means this is our x, 2 is our x, 4 is our y. Has not changed what it means. It's just a different way to write it. We're going to separate these variables in this differential equation. So again, I have dy equals y minus 1 over x times dx. Okay, now I need to get this x. I have to keep this x on this side with this dx, but I have to get this y minus 1 to the other side. How would I do that, you say? You would divide. Divide both sides by y minus 1. That would eliminate this in the numerator and put it over here. So I'm going to show that by this. So I divided. This is left now when I divide this. This is just a 1 up here. So this is what I'm left with. dy over y minus 1 equals 1 over x dx. Again, divided both sides by the y minus 1 because it's in the numerator. Before something was in the denominator, we had to multiply. Now we're dividing. Same thing. What are we going to do here? We're going to take the antiderivative of both sides. I will do the hard part for you. Here is the antiderivative of 1 over x. You all know is the natural log of the absolute value of x plus c. How about over here? The reason why I've waited to this point to do this is because even though it's necessary, this is actually something that we learned, u substitution. We can make u y minus 1, put it over here on the side. Du is just 1 dy. Okay, so then I'm left with here, this is really just the antiderivative of 1 over u du. Well, we know 1 over u du, it's natural log, just like it was over here. So this actually becomes the natural log of the absolute value of y minus 1. You remember why natural log has absolute value, hopefully. Now this is the new stuff. Now we have this different solution. I mean, we're on our way to our solution. We have the natural log of the absolute value of y minus 1 equal to the natural log of x plus c. I need to get rid of those natural logs. How do I get rid of those natural logs? I'm actually going to move this over a little closer. Not all that, just this. Yeah, I know you're laughing because I can't get it over there. There you go. So, how do I get rid of these natural logs? If you were thinking, or if you would have said, raised both sides as an exponent of e, you would have been correctamundo. If you look, e, now why? I'm going to do a little aside. E to the natural log of x, because of the fact that they're inverse functions, equals x. The same goes for the natural log of e to the x is equal to x. Or whatever this little quantity is up here, and I really wanted to change color, you saw me go up there, ends up being this. So in this case, we have e to the natural log of y minus 1. That means these guys, the composition of these two functions allows me just to write it as this equal to, now this is a little different, alright? Here is one little aside that I did here. I'll put that up there, and I'll put a little box and say, okay, remember this. The other thing is, look at this. There's a property that you learned many, many moons ago that x raised to the a power times x raised to the b power is equal to, since we're multiplying like bases, we get x raised to the a plus b power. We add the exponents when we are multiplying like bases. We're going to go in the backwards form of this. Backwards. So here we're already adding the exponents. So we're going to rewrite it as e to the natural log of absolute value of x times e to the c. C representing a constant. So we have y minus 1, the absolute value of y minus 1 equals e to the natural log of x times, and again, we're just using this little property right here of exponents to do that. What is e to the c? Well, e is 2.718281828459045 ... raised to some constant, which is going to give me another constant, which allows me to do this. Just another constant. The absolute value of y minus 1 equals c times e to the natural log of x. That's what allows me. At this level, we are going to use our initial condition and solve for c. I'm going to move on to the next screen, though, So the absolute value of y minus 1 equal to c e to the natural log of the absolute value of x. If you remember, our initial condition was f of 2 equals 4. I'm going to go back to my black color here. There you go. I plug 2 in for x. I plug 4 in for y. Oops, I forgot to do something here though first. I'm sorry. We could rewrite this. I apologize. Let me backtrack real quick. We can rewrite this, use that same inverse property, and write the c e to the, and some of you probably thought, hey, why didn't we just do this? Well, we can. We can write it as the absolute value of y minus 1 equals c times the absolute value of x. We can do that. Now we're going to plug in our 2 and our 4 in here. 4 minus 1 equal to 2 times the absolute value of 2. This ends up giving 3 equals 2c. And c is equal to 3 halves. Alright, so that means we end up with y minus 1 equal to 3 halves absolute value of x. We can drop the absolute value on this side because of y being 4, it's going to be positive. And then to solve for y, we just add 1 to both sides, and we're left with our solution to our differential equation as y equals 3 halves the absolute value of x plus 1 is the solution. Well, this is Differential Equations 2. It's a video. I hope you enjoyed it. It talked about solving some different types of differential equations. We also learned a couple things while we actually kind of used stuff that we've learned in the past. This inverse relationship between e and natural log and the property of exponents. So look forward to Differential Equations 3, where I will do another example on that. So go ahead and look at Differential Equations 3. We'll do one more example related to this. Johnstone, out.